So as you mentioned, my name is Adam Wenchel. I'm the CEO of Arthur, and we are a platform focused on providing observability for production machine learning and AI systems. And so what we're going to talk about today is, a lot of what you learn about model performance and accuracy metrics and things like that in school are only this beginning of what you need to really think about ML performance in the real world. And we'll talk about some of the challenges as well as some of the solutions there. So just to kind of paint a little bit of a picture, I think everyone here is probably very convinced about the potential for ML, and we see headlines like this all the day, every day. This is from an article I was reading Monday about the rise of predictive models in healthcare, and we've seen firsthand the power of some of these models in doing things that really benefit everyone, right? And so one of our favorite classes of models is predictive health models that tries to predict are people at high risk for heart disease or diabetes or sickle cell anemia or some of these other problems. And doing that, not only does it reduce health costs for the companies providing service, but more importantly, it leads to much better outcomes for people and much longer, healthier, fuller lives. And these are the kind of use cases that are really get us excited about in ML. And so, in school, you're taught, like, if you were to say, let's say you were tasked with developing a model to help predict which of your patients or which of the people that you care about are going to are at high risk for heart disease. And you probably start with a nice big label training set where you have several years worth of data on patients, outcomes, and who developed heart disease and who didn't to train your model on. And if you've taken any sort of machine learning coursework, all these metrics are going to look very familiar to you. And these are the ones that you'll select. And so typically you'll take part of your training set, the bulk of it, maybe 80% of it, and you'll train your model on that to find the patterns and get good at predicting who might develop this condition. And then you'll reserve a portion of it, say 20%, for then testing that trained model and saying, all right, how many with that 20% of the data, how often was I able to correctly predict that the people who are at high risk? And that's great, and these metrics are really wonderful. But the question is, like, let's say you train this model, you're at 95% accuracy, which for your purposes, let's say is plenty sufficient, and you're ready to deploy in the real world. Is that enough? And so a little bit of a spoiler alert that it's not. And we'll talk about where the challenges come in when you actually go to deploy this in the real world around performance and accuracy. So just to kind of set that up, first thing, one truth about the world, one thing I'm very certain of about the world is that it never stands still. It's not a static place. It's always evolving and it's always moving. And we've seen an amazing example of that in the last year or two, obviously with COVID and the pandemic striking. This is just a graph of vehicular traffic data that I pulled for an example, but the light blue lines is 2019 data and the dark blue line is 2020 data. And you can see, like, chugging along through February, they were matching up really closely, very similar. And then all of a sudden, the world changed. And all of a sudden, the data began to look very different. And we've seen examples of that, whether it's like people's spending habits or their healthcare habits or their travel habits, like all these massive shifts that just happened really quickly. And this is really critical because, when you're looking at the historical data, like one really common paradigm is to look back at the previous 2 years. That way, if you're using ML for a use case where annual seasonality plays a part, where you might have like peaks around the holidays or in summer, you need that kind of perspective. And so, but the challenge is 2020 did not look much like 2019 or 2018. And some models were fine. They weren't that affected by it, but other ones were significantly impacted by it and really struggled to adapt. And being able to kind of detect that quickly is the challenge. And so, at Arthur, when we think about sort of these problems, we can kind of cut them up into 3 different categories that are very scientifically named: slow problems, fast problems, and very fast problems. And so just to kind of characterize each 3 of those, the slow problems are, like just the general change of the world. These are kind of long developing shifts, like macroeconomic shifts that may take years to play out, or population shifts as people move around. Just kind of, like styles change, things go in and out of style, like all this stuff. And those can take years and even decades to happen. They're always happening, but they happen relatively gradually. And they do affect models, but not suddenly. Then you have fast problems. And so the pandemic that we mentioned, that's a good example. But sometimes it can be stuff closer to home too, right? So all of a sudden, your marketing department decides to market to a different demographic that it's never marketed to before. let's say, different age range or something like that. And all of a sudden your model is being asked to reason about a category of customers or of applicants or patients that doesn't really have, or not well represented in your training set. And the model really doesn't have a lot of past historical knowledge about, and yet it still has to make decisions. And then the last set of problems are these very fast problems. And so these are things like an upstream data provider makes a change to the way the data is encoded, and all of a sudden it starts coming in a little bit differently. And so one of my favorite examples, one that I've been personally bit by, was we had a model once that was for one of the features. It was getting a continuous numerical value between 1 and 100, so always positive. But sometimes it could be null, and that was fine. We built our system to be able to handle those cases. But an upstream developer made a small inconsequential change to the system where all of a sudden the nulls, instead of coming through as literal nulls, came as -1. This is a common developer paradigm convention. And but our model went ahead and kept reasoning about these -1s as if they were continuous numerical values, even though in the training set, there were no -1s represented, and this value, kind of to make sense, had to be a positive value. But a lot of times these ML systems, these models will go and continue to make decisions. And as you can imagine, the accuracy for the decisions on data points that had this -1 null were not very high. And so those can strike at a moment's notice and drastically affect your performance. And then one interesting side note to this is sometimes the slow problems are the ones that have the biggest impact because they are significantly less dramatic and they happen so gradually that your model can just very slowly degrade over weeks or months or even years. And it doesn't get caught because it's not a drastic shift in performance. And so those ones can sometimes be the most insidious of all. Then let's talk about a second truth of real world systems. And this one's not 100% true like the first one, but it's true awful lot of the time, which is, when you think about kind of deploying this, you train your model on a historical data set, you deploy it and you start making predictions, and then you get the results and you say like, all right, as I'm making these predictions, were they right or were they wrong? And then ideally you would use that information about how many got right, how many got wrong, and feed that back into the training set as additional label data and information about performance. And that sounds nice on paper, and in academia, this is sort of the vision they present, but it turns out that 90% of the time this doesn't work. And the reason is this feedback loop ends up being, A, it's rare, oftentimes it's not present, and B, a lot of times, even when it is present, the timeline to getting that feedback is so long that it's not that valuable. And so if you think about predicting someone's risk for heart disease, you may be predicting that over the next 2 or 3 years, they'll develop it. And so if you wait for 3 years to say, all right, did I get that prediction right or not? And it comes back and it turns out your model's been wildly inaccurate. Well, you've been making terrible decisions for 3 years. And so you can't wait that long to start reasoning about model performance. And so you really need ways to think about model performance that are much quicker and much faster, and that don't require a 3-year delay or a long delay to get that feedback. So that's all the problems. Let's talk about some of the solutions. And roughly speaking, these are just sort of like the basic blocking and tackling that you want for production ML systems when you're putting these models in production. So the first one is just to set constraints on the data. So if you know that a field must be between 1 and 100, absolutely put those constraints in so that if you all of a sudden start getting 150 or -1, that gets rejected and an alert gets sent. The second one, and this is really one of the powerful ones, is around this notion of data drift, and this is a really critical thing, which is if you look at these figures here, these graphs, characterizing how close is the distribution of data that I'm seeing in the real world that I'm being asked to make decisions about to what I trained off of. And so if you think about kind of the distribution curve of the ages, let's say as in this first example here, in your training set, if that starts to shift, then you need to, your model is going to degrade. Performance is going to go down. And so you want to watch for these shifts in your data. And those are like almost always like leading indicators of performance problems that you can get like immediately without having to wait for any sort of feedback on model performance and accuracy. And there's a lot of different techniques for calculating this data drift. It's a fast talk, won't go into all of them, but things like KL divergence, KS test, PSI, population stability index, are all great tests. They all have kind of subtle pros and cons, and there's sort of applicability in different situations, but it's, having some coverage of your inputs, any coverage will make a huge difference in your ability to detect these problems quickly. And then the last one, of course, is just anomalies. Like a lot of times you end up with features where, while the range of possible values may be 0 to 100, like 99.9% of the time, you're going to be in a relatively small range of that. And so you may just want to kind of flag ones that come through as very unusual, the corner cases, for someone to take a look at just to make sure they're not indicative of a bug or a larger problem in the system. So that's on the inputs side, the data flowing into the model. And then let's take a look at the other side, which is the outputs of the model, right? The predictions. And what do you want to do with those? Well, it's a very similar story. So think about constraints again. If you're predicting a credit score, well, we know credit scores can only be between whatever it is, 200 and 840 or something like that. Don't quote me on that. And so if your predicted value is outside of that, that's a problem. And then prediction drift, which is sort of the analog of data drift, this is sort of saying, hey, if the distribution of the predictions coming out starts to shift, like I should know about it. That should be something I need to take a look at, right? And so if I have an animal classification engine that all of a sudden, one day 30% of the animals I'm seeing are dogs, and the next day it's like 80%. At a minimum, I should look into that. Maybe there's legitimate reasons for it, but it's definitely signs that something's changing and there's some instability that I should look at. And then you can also, that's kind of just to look at it straight, like something like classification rates. But you can also look at the distribution and use those same kind of distribution comparison metrics that we talked about before, like PSI, on the outputs of your model, a regression model or a classification model. And then lastly, anomalies, again, similar story. If you have outliers in your predictions, you're going to want to take a look at those and really understand them just to make sure that they're in line with expectations and reasonable predictions. And so what I just described is the basics, and that will get you a large part of the way there towards being able to sleep at night, knowing your systems are working well. But there's a lot beyond that as well. And so just a couple of things to mention, a few. Multivariate drift. So, on that animal classifier, you may have a lot of animals with paws coming in and a lot of animals with feathers coming in, and you can measure like what's the rate of feathered animals that are coming in. But if all of a sudden you start getting an animal that has both feathers and paws, that's a problem, right? And so moving beyond kind of univariate notions of data drift into multivariate notions of co-occurrence and drift is really powerful for, if you want to take it to the next level. And then the other thing I'll mention is regional performance, right? So understanding not just the performance of your model overall at a global level, but understanding it like different pockets of the data, different categories of your population that you're being asked to reason upon, how accurate or inaccurate, how much drift are you experiencing? And this can be really important because oftentimes when you experience data drift, the initial response is to do a refit of your model because the data's shifted, let's refit it on this the new normal. But regional performance can give you really good indication that maybe there's some additional featurization work to do. So if you're consistently doing better at predicting, credit scores for people in the older part of the population, but you're doing a terrible job at the people in the younger part of the population, maybe it's because your features aren't adequately capturing what makes someone in the younger part of the population a good credit risk or a bad credit risk, and so you really need to rethink some of that feature risk. Or some of the featurization work that you've done and improve it so that you can make sure your model is like performing well across the spectrum and not just in different pockets. And then we've talked a lot about structured data. I just want to kind of throw out there that this also affects unstructured data quite a bit, and it gets a little more complicated to reason about. But if you think about computer vision, right, like how do you kind of approach these problems of drift, whether it's NLP or computer vision, when it's just a stream of characters or words or a stream of pixels, and that gets a little deeper into math, something we spend a lot of time to make sure that we do well. And but it's important because sensors change, cameras change, what the world around these things change, and so it's really important that you apply this in all different domains, whether you're doing NLP, computer vision, or other forms of unstructured data. And then the last thing I'll just tee up for a future talk is, this performance monitoring is critical as the foundation for kind of broader observability, which, if you really have a production ML system and you want to make sure that, it's working well, in addition to like understanding the performance and making sure it's performing well for everyone, you want to be able to explain what it's doing. If it's affecting humans, you want to be able to check for bias and mitigate any bias potentially. And then the last thing is, if odds are, if this is a system that has a lot of leverage, it's affecting a lot of people, a lot of revenue, that is part of a larger organization. And so really taking all of this knowledge and this monitoring and operationalizing it in a way that different stakeholders across the enterprise or the company can use, whether it's business people or analysts or compliance people, and really making it actionable by everyone. So just to circle back, I think that we just see, like at Arthur, we're super excited about the transformative potential for all of these things. We really believe that we get excited when we see some of what our customers are doing with ML and the ways they're deploying it to benefit the company and the customers they serve. But in order to do that well, in order to kind of really capture that potential, you need to put it out in a way that you can trust it and that it's performing well, that it actually is performing well, and not just kind of throwing it over the wall. And so, these are important issues to think about. But the good news is, if we get them right, then the potential to really be successful in these systems goes up. I mean, this is like the thing I see that really kind of is the most powerful in terms of creating real world value and why we get excited about it. So I think with that, I will stop there and open it up to any questions. I think we're about at time.